So now let's take a look at an example problem. The elastic portion of the tension stress-strain diagram for an aluminum alloy is shown in the figure. The specimen used for the test has a gauge length of 2 inches and a diameter of 0.5 inches. If the applied load is 10 kips, determine the new diameter of the specimen. The shear modulus is G equals 3.8 times 10 to the third KSI. Before we begin solving for anything, let's use the given find solution format to determine what information we're given and what we need to solve for. We're given the gauge length, also known as the initial length, of the specimen, which is 2 inches. We have the initial diameter, which is 0.5 inches. The applied load P is 10 kips, and the modulus of rigidity is 3.8 times 10 to the third KSI. We need to find the new diameter of the specimen after it undergoes tension. Let's start by finding the modulus of elasticity. Remember, the formula for that was given by Hooke's law, which is stress equals modulus times strain. The stress-strain diagram gives us a random point on the graph that we can use to plug into the formula. According to the diagram, we can plug in 70 KSI for stress and 0.00614 inch per inch for strain in order to calculate the modulus of elasticity. After dividing the two values, we get 11,400.65 KSI. Now let's find the stress caused by the specified applied load. Remember, the formula for stress is applied load divided by original cross-sectional area. The cross-section of the bar is a circle, whose area is pi over 4 times the original diameter squared. Plug in 10 for P and 0.5 for the diameter, and we get 50.9296 KSI for the normal stress. Next, let's find the longitudinal strain. We can just rearrange Hooke's law again to do this. We'll plug in the 50.9296 for stress and 11,400.65 for the modulus to get 0.0044673 inch per inch. Note that we have 2 out of the 3 values that describe the mechanical properties of materials. Do you remember the equation we can use to find the third value? It's G equals E over 2 times nu plus 1. In this case, we know E and G, so let's solve for nu. Once we do that, we get nu equals 0.5. Great! Now we can find the lateral strain using Poisson's ratio. We'll need to rearrange it a bit since we only know the values for Poisson's ratio and the longitudinal strain. If we multiply these two values and negate it, we get negative 0.002234 inch per inch. Almost there. Do you remember the equation for strain? If you need a refresher, be sure to check out the key concept video for Chapter 2 on strain. It's new length minus old length over old length. In this case, though, the length we're dealing with is technically the length of the cross-section. Since the cross-section is a circle, the length will be the diameter. We can rearrange the strain equation to solve for the change in diameter, denoted by delta. We'll plug in 0.5 for our original diameter and negative 0.002234 for our lateral strain to get negative 0.001117 inches for the change in diameter. Lastly, we can solve for the new diameter. The change in diameter is just the new minus the original, so we'll again rearrange the equation and plug in our values. For our final answer, we get that the new diameter of the aluminum alloy is 0.4989 inches. Note that the new diameter is smaller than the original diameter, which was 0.5 inches. This is because when the specimen is in tension, it elongates longitudinally and therefore contracts laterally. Since it contracts laterally, the diameter should get smaller, as it did. And that's a wrap. I hope this two-part lecture and example series helped bridge the gap in your understanding of the mechanical properties of materials. As always, if you have any questions about what we reviewed, feel free to ask in the comments below. Thanks for watching!